pick up at smaller scale than what Pierre has talked about. Pierre's talked about larger scale aspects, and tomorrow I'll talk about also mud flows and debris flows, which are very common here, but the material is ice. And I'll show some examples of one of the major causes of flooding around here is mud flows. Talk about that tomorrow. But today I want to talk about contraction scour, and I want to inform you that I was invited to a symposium of obstetricians and gynecologists because they saw the word contraction in the keynotes. And they thought immediately, this guy needs to submit an abstract with a paper to this conference. So I was tempted, but yeah. Purpose of this lecture is to talk about the hydraulics associated with contractions, and the loose boundary hydraulics, but also the fixed boundary hydraulics, because I think they'll be misunderstood. And in particular, I'll talk about bridge waterways, which rely heavily, which contract alluvial channels for reasons of bridge construction, which I'll explain tomorrow. And so contraction scale you need to predict in order to predict the abutment scale accurately. Then I'll define short, intermediate, and long contractions. And up till now, literature has dealt with inaccurately, I think, with short contractions and long contractions, which you go back to Straub and Lawson, they talk about long contractions incorrectly. Most of the contractions are short contractions. Bridge contractions are short contractions because the bridge is quite short compared to the channel width, typically. But I'll talk about experiments which we did at CSU, where we use intermediate length contractions. And intermediate contractions are important because the control is downstream, not at the bridge opening itself or the contraction opening, typically. And long contractions, I'll explain that in due course. And I'll mention the limitations of these, and I'll show a number of large-scale flume experiments which we conducted, live bed in Clearwater, on contraction scale, and some of the findings from the experiments. Most bridge contractions, for instance, most bridges, I should say, are contractions, as you can kind of see here. Contractions occur naturally in channels for reasons of geology and so forth, morphology of the channel is contracted. So typically, a bridge is a classic location of a contraction. You can see that's a short contraction. The bridge width is quite short. And the reason that bridges are contracted is because it's cheaper to build in that way as contractions. Cheaper to have an earth-fill embankment right up to the hard, rigid bridge deck, and then earth-fill embankment on the other side. So, as I'll explain tomorrow, the contraction part is where bridges typically fail. So this is an example of a bridge in Iowa which failed. In contractions, the flow doesn't like contractions. It wants to erode and open up contractions always. So the contractions are locations of erosion, particularly. So this is a bridge where the earth embankment, and this is showing here the typical location where most bridges fail. 90% of bridges fail at this location because it's very hard to combine an earth fill and a rigid structure together. It's a problem for dam building, earth fill dams and spillways and so forth, but I'll go into that tomorrow. So in order to predict the scour that we can get at a bridge abutment, we need to know how much contraction. And estimating contraction scour is very difficult. So the talk that I'll give this afternoon is not necessarily, I don't have all the answers, but I'll show you some of the complexities and show you some of the thoughts that we have. So contractions involve both hydraulics and rheology, in particular geomechanics. And personally, I think a lot of the future in civil engineering is combining civil engineering more with other fields, such as atmospheric science. If we talk about climate change, you need to know what are the climate process, what are the oceanic currents involved. Same with bridges, we need to combine hydraulics and geomechanics. So putting riprap here on the slope does nothing for geomechanic strength. It weakens that embankment, if anything, because you're adding dead weight, not strength. Anyway, we'll talk about that tomorrow. But this is a contraction. You can see the earth filled up to the bridge deck, which is the rigid part, and earth filled on the other side. This is a small creek or river in New York. Bridges are short contractions, as you can see through here. Earth fill embankment, bridge deck across here. Complicated flow field. They contract the flow, obviously. and they generate and disperse large-scale turbulence all the way down. So all this has a bearing on the alluvial channel over which the bridge is built. And so bridges also on floodplains, and most bridges these days, if you have a floodplain on a channel, you have the bridge abutment back from the edge of the channel in order to keep a passage open for an environmental passageway here and be able to drive a pickup truck if you have to. So we have the main channel here and the floodplain here. This is the plan view, but you can see the highly erosive nature of the flow contraction, the turbulence generated through here. So there's a lot of interest in contraction scour at bridge engineering. The flow is most erosive over here because of the contraction and the turbulence, but the boundary is most erodible here in the main channel because it's typically looser than on the floodplain itself. There's more cohesive material, more vegetation, more binding. Well, I'll talk about that tomorrow. So we can get scour at various locations, both here and here, based on flow erosiveness, boundary resistance to erosion, and boundary geotechnical stability. Because as soon as you cause erosion to occur, then you have to consider geotechnical factors in terms of what slopes are stable, slope stability. And in my opinion, hydraulic engineers don't get enough together with geomechanic engineers as well as geomorphologic engineers. So this is an experiment which I did in Iowa. You can see the flow contraction through here. This is an erodible embankment, a bridge abutment column, which I'll define tomorrow's talk. But you can see the flow coming over the floodplain and contracting into the main channel here, a dead zone here where you get sedimentation, perhaps, but you can see the failure here. And later on, tomorrow, I'll talk about the modeling of earthful structures, how you handle that or try to handle that in hydraulic models, as well as hydraulic modeling criteria themselves, which I think are open to question. We've accepted them quite extensively, but they are open to question. So scour is deepest, the region of greatest contraction, I should say, right here. So the contraction scour here. We have geotechnical failure of the embankment. If we have a rigid structure here, we have scour, which is deepest around here because the flow velocities greatly contracted. Flow is greatly contracted and flow velocities are higher and more turbulent structures. So I'll talk about an old adage, and this is a problem, contraction scour analysis. The adage is depth attracts flow, as I mentioned before. So if you want to determine this is a bridge in Alaska with guide bunds here and spur dikes with heads to really cross a braided channel of the low river. And so the difficulty of determining contraction scour for many bridges is when the bridge opening is not fully contracting the flow. And here depth attracts flow. Flow is deepest here. The flow is always attracted to that point there. Now, a bit of open channel flow theory. For a contraction, we have and I'm just going to deal with 45-degree vertical contractions. Contractions very much depend on the shape of the contraction entrance, of course. But the flows come in through a rectangular channel, as you'll see, experiments I'll describe. There's flow separation occurring here, which generate a lot of turbulence, as you'll see. Flow is very unsteady in this region here. And the actual contraction is much narrower here than in the width of the narrower channel B2 down here. So these are the general features of flow contraction. Then you have on top of this an alluvial erodible boundary. How does that adjust? In the past, if you go back to Straub or Lawson in the 1960s, although in the late 1980s, he realized there was a mistake in his contraction relationships, his papers, and Straub. They talked about, for Clearwater scour and live bed scour, short contractions, i.e. at a bridge. And they described their contraction relationship as really not applying to short contractions because of the turbulence, which I'll illustrate, but more to long contractions. These days, we would say that the intermediate contraction needs to be considered very much, and the control for this contraction is at the downstream end of the contraction. From fluids, from hydraulic engineering, the controls for a subcritical flow at the downstream end, not the upstream end. So a short contraction is 1 to 2 times the width of the approach flow channel, so it's shorter than the vena contractor itself. So the short contraction is less, the flow separation goes beyond the, say, a bridge, for instance. Intermediate contraction is when you have a contraction and the flow separation area is not as long as the contraction itself. And a long contraction goes, you have a flow is contracted, comes in here, and then down there, you have uniform flow conditions. So the control is the uniform flow condition down the end there. So you don't really have choking, which I'll talk about soon at the downstream end. We talk about short, intermediate, long. I tried to put some definition in terms of the separation zone, but they're kind of loose terms. Most bridges are short contractions. They form contractions go beyond the bridge deck, so they form intermediate contractions, but intermediate, which are important in terms of control. So this is the short contraction. Intermediate contraction, where we have the flow coming in, you have control down here, because you'd lose like a local energy loss at the entrance, you lose friction energy loss, resistance to flow along the contracted channel, and you might have an exit loss here as well. So this part here is the first to choke, down here, not up here. Whereas for a short bridge, this is the resistance part is negligible, and choking typically occurs within here, as I'll show tomorrow. For long contraction, then you have choking at the upstream end, perhaps. But if the channel is infinitely long, say you have uniform flow conditions. Most rivers don't have uniform flow. They have flow, which is because the geometry is changing all the time. But anyway, we have these, we've decided to have short contraction, intermediate contraction, long contraction based on this. And the experiments that I'll show you are intermediate length. The relationships from Straub and Lawson deal with long contractions. But bridges typically are short contractions. And they are short contractions marked by turbulence. So if we look at the short contraction, for example, in plan and elevation view, we look at the specific energy diagram, if you remember that from hydraulic engineering. First of all, you find with a short contraction, you have a non-uniform flow, an M1 curve, a backwater curve at the upstream end. So what flow depth should you use in determining contraction? The bridge designers use this depth, which is part of the M1 curve. It's not uniform flow. You should really use the YN2, the normal flow depth upstream, although it's kind of a fiction in a way for real channels. This is under the bridge deck. We have an M2 curve, you'll see from the intermediate curve, and I follow the specific energy diagram down here. You go back, and it loops back up to the channel continuing on down here. Normal flow depth is occurring down here. So these figures sort of show for the short contraction. If we have an intermediate contraction, we have an M1 curve. Depends on how much we contract the channel with. So the lines vary a little bit here. Then we have this M1 curve is the most common unsteady flow profile. Second most non-uniform profile is the drawdown curve, the M2 curve. So we draw down. So the flow is not necessarily uniform through here, right down to here to the exit, and then we carry on down here to the normal flow depth. We typically lose energy as indicated through here. So that's the intermediate flow condition. For the long flow contraction, we have on the specific energy diagram something like this. So we have the M2 curve, we lose energy, we have a depression in the contraction, and then we get down here uniform flow depth. This is the long contraction. So contractions, we have these three conditions: short, like at a bridge; intermediate, which is not that common but can occur; and long, which is not that common but theoretically can occur. Choking is very important. So choking relates to the throat. If you narrow the throat too much, you choke. And so you can't get the flow in. So you choke, it means you have to back the flow up, and then you get enough head to push the flow through. So you know from the specific energy diagram where we get down right to the point here, we have choking. So if those contractions lose energy, the contractions and the resistance together and the exit loss push us all the way down here, we can get choking at the downstream end of an intermediate channel, which I'll show soon. So for short length contractions, we get choking at the entrance. Intermediate contractions first at the exit, the downstream part of the contracted channel, then at the entrance. Long contractions, we get typically contractions at the entrance. And this needs further work, I think, but that's our thinking at this particular point. And you can show, particularly through running 1D model like HEC-RAS, and go beyond the shear stress ratio that we had in the model. Our experiments went up to not that far, actually. The numerical experiments went that far, but you choked and no choking, you can have these sorts of zones, B1 upon B2 upon B1 over here. You can describe when you have choking and no choking. So most of the prior literature mixes these two. So you have, for different values of B2 and B1, you'll find in the literature, as I'll explain soon, a mixture of choking conditions and non-choking conditions. So the literature is not to be trusted. So this is choking, and choking some bridges, particularly for short span masonry bridges. Half the bridge stock in Ireland are short span masonry bridges because they were the easiest to build. You just pile rocks and make an arch. But over time, with urbanization, the flows have increased with increase of loading as well. These are bridges that are over 100 years old, typically designed for, say, a small vehicle, a horse and cart. You have trucks going over them. They choke quickly, and culverts often choke. And so you go right down here, choking occurs, and you go back up here, and you'll get inlet control basically for a short span bridge, like a masonry arch bridge, or most culverts designed that way. And so downstream choking, we look at intermediate contractions. That's choking down here because we have energy loss here, local energy loss through flow resistance here, which is usually quite small but not negligible. We can have energy loss at the exit as well. So we first choke down here before we choke up here. We can get upstream choking too. If we narrow it too far, we can get choking right at the entrance here too. This is upstream choking. So these intermediate length contractions have both upstream and downstream choking, which differentiates them from short contractions and long contractions. So the bed is alluvial, the bed is erodible. The banks are erodible too. And so that's where, if we get any sort of scour, you quickly have to get geomechanics into the picture. And that's one thing we learned in the in-stream structure, the rock veins and the Benway weir type thing. Didn't take much to fail those structures, typically. Once they failed, they were kind of stable, but still, they failed readily. In the experiments, we keep these rigid. So I won't consider rigid wall, but I'll show more tomorrow. But you'll see that we have a vena contractor. The flow is contracted, comes around here. It doesn't make a 90-degree bend and flows down here. It spreads out, reattaches here. For a narrow contraction, the bridge or the contraction is shorter than the vena contractor. Most numerical models don't handle contractions and loose beds very well yet, in my opinion. Most 2D models for sure, and 3D models, I have my suspicions. They don't handle this very well because I've tried them, and I'll show you soon where a classic example where a good 3D model could be used, has to be applied, and I had a student apply it, but it didn't work very well. Maybe he didn't mesh all up. So previous studies, if I go back to Lawson, Straub, they talked about and they focused on that. And that's a classic. You follow Straub's paper, or Lawson's papers, for example, on clear water and live bed scour. You basically narrow the channel and you recalculate the shear stress on the bed. And you determine how much the bed is lowered. Nothing about intermediate here. Bridges, though, are short contractions, I should say. So these are some of the previous examples. And I won't go through each of them. Straub, back in the 1930s, did some interesting experiments right through all of these. Webby's is used extensively. New Zealander, some papers on Chinese. Lawson, who is not included up here, these are live bed cases. He did no experiments whatsoever, except till the late 1980s. Then he had it with a graduate student. Then, as I'll explain soon, you get a trend when I talk about long-term trends in contraction scour that we saw in the experiments, which differed from what he originally put in his papers, which had published in the 1960s. The main findings in the previous studies, an adequate description of contraction hydraulics, in my opinion. Most of them really had short contractions, as they talked about long contractions. They were done in small flumes. Slight of any improvement of Lawson's 1960 work, in my opinion. Lack of a reliable database because they mixed choking and non-choking conditions. So you have differences in flow. You're comparing apples and oranges. Here are some of the uncertainties, some of the data plotted, and sources of uncertainty, choking, different sediment sizes, and so forth. Various contraction lengths, unknown length of location of measuring depth of contraction. This is a problem, as you'll see soon. Where do you measure contraction? Because you have bed forms. Do you measure them at the top, the middle, the bottom? Do you measure them along, middle? It's actually quite difficult to do contraction scour experiments. A lot of inaccuracy involved in figuring out where the contraction depth really is. These figures just show some of the data. This just shows a mixture of choked and no choked conditions. If we look at HEC 18, which is the Federal Highway publication on Scour, this is the relationship they use. It doesn't talk about vena contractor at all, the narrowing of the flow in a short contraction and then the widening. So this relationship here, which is okay, but there's no, and I'll later show a correction to this. This equation is easy to use, so it's very appealing to most consultants based on sediment continuity, what goes in goes out, total sediment transport, shear stress, variation with narrowing of the channel, Manning's resistance equation, but no experimental data to support this equation. But it's nice to use, and people like equations that are nice to use because they give them a good feeling and the client a good feeling. You go in here in court, then the jury has a good feeling too. But the equations, the exponents, and are questionable. What are its limitation? Where does it apply? The exponent P, for example, deals with the Rouse parameter, which here. So different types of motion of bed material you would plug into this equation, and you get an answer. And for most engineering purposes, perhaps it's okay because we don't know for sure. And nobody's going to check in the reality, in the real world, and get reliable measurements of contraction scour. Anyway, I'll talk now about some of the flume studies, which will give you an idea of what we saw at CSU. This was a project done for the NCHRP, the National Cooperative Highway Program. All the DOTs pulled money and figure out what topics are important. So we use this large flume here, 200 feet long, 8 feet wide, 4 feet deep, which is given to us by the USGS. This is an old USGS flume. The USGS was also based in a lab at CSU. And we put in contractions, both a very narrow, with a quarter of the width, to medium, half the width, and typical bridge, perhaps 0.75 of 3/4 of the width across, and about 80 feet, I'll give the dimensions soon, but 60 to 80 feet long, I've forgotten. And this flume took a lot of sediment. And I tell you that many students think they're working on their PhD, they're going to learn sophisticated stuff. Instead, they do a lot of shoveling, shoveling of sand and so forth. I tell them they don't need a gym pass, because every experiment, they have to re-shovel the sand. They have to load the sand in the flume, or reposition it back. This is a picture of the flume experiment, the flow coming out of a tailgate at the end of the contraction. This is a narrow contraction. This is an elevation, a plan view, an elevation view here. And we've exaggerated the vertical scale just to make it clearer. And this flume is not recirculating sediment. There's not that many flumes around that recirculate sediment because you need special pumps that can handle that as well. So we had a sediment hopper here to feed in the sediment. So the question then is, well, what rate should we feed the sediment in? And I'll come to that soon. And this is the 45-degree vertical wall, as you see here, the contraction along here, and then a sluice gate to kind of set initially the things all up. A sediment trap here, and then the flow pass through pumps, small sump, and then back to the head box upstream. Sand. Took about 6 dump trucks full of sand to load up the flume to do this experiment. So I was not joking about the experiment. These students, a couple of them had to do a lot of shoveling, and they were at first cursing me they thought they'd be doing something sophisticated coming to the US. They were foreign overseas students. Instead, they end up doing a lot of shoveling of sand and patting down and making sure it's all uniform. And what you find is it's very hard to buy uniform sand in that volume. You have a small amount, fine. But if you're talking about 6 dump load trucks, you're shoved this end of the spectrum in terms of size distribution. You can't find a uniform medium sand unless you're prepared to sieve it yourself. And I've done a lot of sieving in my time. Down this end of the particle size plot, the provider sends you a curve like this. You take a couple of samples, you find actually the D50 is a little bit, maybe less, could be more. Stuff is not as uniform as you thought it was. Anyway, we ended up with the sand, these 2 curves here, which we tested, which we had delivered about 0.26, about a medium sand into the medium fine sand upper range. And it's hard to find a sand around here which doesn't have magnetite in it. That's the black sand. But the concentrations, fortunately, are relatively small. So you'll see patches of black picking up here and there, which to me actually are quite useful. All to say that to find that volume of sand, uniform sand, is no trivial undertaking. So this is the instrumentation that we used. We used LiDAR, which we scanned from both ends. platform set up here. We used LiDAR a lot. LiDAR is very useful. We use drones increasingly to take photographs of experiments which are hard to take photographs of. We used ultrasonic devices and master probes for looking at the water surface. We thought we could track what was happening with the bed using CTEC ultrasonic transducers. But because we had a rotating flume, the water warmed up. As the water warms up, the sound speed through water changes. So you can't rely on getting accurate values of water depth. The bed was going up instead of, we knew it was going down, but these things were telling us that they're going up. So we abandoned these. We got lots of data, and this gives you some of the background. Then the question of, well, how to get the sediment into the flume and what rate to match the flow rates and to be sure we weren't putting too little or too much sediment in. And that's, quite frankly, a matter of guesswork. We were fortunate that the same flume had been used by Guy et al. Back in the 60s, using essentially the same sand size to create this sort of plot. If we use Larson's relationship or Hick-Raz and so forth, we'll show one of the relationships in there, we get these plots. So you can see the big difference. So log-log plots are commonly a butt of joke with regard to sediment engineering. People always show log-log plots, and if you're off, you're easily off by 100% or something like that. Anyway, we chose to go with Guy's feed rate in terms of feed rate versus discharge. We went with this, and then you have to spread it across, and you have to be sure that the sediment, this is 0.2 millimeters, in fact, hits the bottom before the contraction. So we had this thing parked up well enough. We had a kind of a chute, and we spread the particles out. Ought to say that doing experiments is not an easy thing necessarily, numerically or physically, for that matter. There are complications, but you have to get on. This is an NCHRP project. We have a deadline to meet, so forth, schedule followed. I used a small hopper like this. The other hopper we had didn't work too well, and a post sediment down here on the upstream end of this other trolley, and fed sediment along the bed. We did clear water and live bed experiments, and so here, very quickly, clear water and live bed experiments, and dimensional analysis, which is a great back of the envelope check that you have the right parameters involved. Even though you don't model many of the parameters, at least you've got the ones that you're doing kind of right. So we looked at depth of scar over normal flow depth, because the normal flow depth depends, if you remember from Manning's equation, really only on the channel properties, the width, the roughness, and so forth. We looked at the width ratio of the contracted channel to the approach channel, particle size over flow depth. We changed flow depth a bit. With particle size, we couldn't do much about. We did change the approach flow, shear stress, live bed, clear water over critical values for and we didn't change these other terms. There are more terms that really should be in here for contraction scale. Also, we wanted how far to go with the live bed scale with the critical shear stress ratio, the shear stress on the approach flow bed divided by the critical value of the material, shear stress for the material. And for that, we looked at a USGS study by Benedict and Caldwell, based in South Carolina. And they plotted things in terms of velocity ratio, approach flow velocity over critical velocity. And they went up to 2.5. You convert that to shear stress ratio up to about 4.6 value of that ratio. As I'll show you soon, you could go higher, and there are consequences. I won't go through this very long, but all to say that we used this fine sediment, we changed the contraction ratio and the approach flow shear stress ratio. We measured these particular locations. This is a squished version of that plan view figure. So first of all, we had to provide, for numerical modeling purposes, flow velocities, which I won't go into. We had a sand bed here, as you can see here, and we put down plywood here just to measure velocity. We didn't want the bed changing while the velocities were being measured. Then we looked at the entranceway here. We focused on that. You can get a sense of the vena contractor and how turbulent it can be, particularly with narrow contractions like this. You have the flow which comes around on a 45-degree bend, very turbulent zone, and you'll have another view of this later on. And then crossing, you get this waviness, so very turbulent zone in here. So you have, as I'll talk about, two zones of scar for this particular experiment, both corner scar around here and vena contractor scar here. This is due to the contraction of flow. This is in particular, the flow contraction, but also the turbulence. Turbulence acts to lift material up off the bed. Very important for scour experiments. Not well simulated in modeling. And these are views of the experiment. Clear water, CW, B2 over B1, 0.25, water of the width, and the shear stress ratio of 0.3. The clear water scour, previous slide I showed the experiment program. A view looking at the entrance and a view looking upstream on the channel. First of all, you'll notice black sand. It's hard to find clear white sand at any volume which doesn't have black sand in it. But the proportion of black sand, which I forget, but it was relatively small, we didn't have armoring. Black sand is twice as dense as quartz sand. It's largely iron magnetite, iron varieties. It results from the igneous rock in particular, I think, around here, which is crushed. But I found it useful because it showed zones of high shear stress. It always collected and was exposed at zones of high shear stress. This is the approach bed, clear water, and this is the bed through the contraction. So you can kind of see here the approach bed through here, and then corner scour and vena contractor scour. So you tell me what the scour depth is in the contraction. It's a heck of a job to say what the contraction scour depth. You measure the bed forms, but they're very three-dimensional here. So contraction scour, very important. And if this was a bridge abutment, which motivates much of the study, then you'd have geotechnical, the slope would be unstable, and you'd have geotechnical issues, rheological issues to consider. So this is clear water scour experiment for that one I just showed. And the first thing you notice is the short scour, you get very deep scour. The vena contractor profiles, which we got through LiDAR, doesn't show the bed forms that well, but deeper scour at the entrance, and then it kind of varied along the contraction. This is the end cell of the experiment setup. This is the time. So it was a very difficult job to show what the vena contractor scour really what the contraction scour actually comprised, even for clear water scour. This is 0.56, so a little bit. It's really hard to keep a clear water area of bed flat. Any little disturbance causes bed forms to develop and ripples. This is the problem with this type of sand, is ripple formation. Anyway, we put up with all that, but again, you see around the corners, you get deeper scour, and the contraction scour in here, the black nicely shows the higher shear stress in there. So you get, I won't say armoring, I don't think it affected the result, but it can show that the shear stresses were higher there than other places. And this is looking along the channel. So very hard to say what the contraction scour is because the flow is not uniform through there, naturally enough. And the black line, you can hardly see, but this is sort of the black line here. So we got scour, the corner scour and the scour across the entrance was pretty much the same. These are centerline profiles for the shear stress ratio of 0.56, clear water scour, height contraction. Would never build a bridge. And this is where you have to reach in your toolbox, and maybe you'd reach for a numerical model because you couldn't really see in the physical model what was going on. So you notice the clear water here and then a step. It's like a step scour or a head cutting type scour. And then because of this contraction is very extreme, more extreme than you'd actually build a bridge. The corner scour and the vena contractor scour were about the same. So we did reach for a flow 3D model to try and, because this is too steep to show, you couldn't see in the model itself what was going on in here. So we thought maybe the flow 3D model would show us what the flow was doing. But the flow 3D model didn't really handle the flow separation, I should say, too well off the edge. Maybe we didn't grid it tightly enough. It remains to be an experiment that can be done by somebody, maybe Yonglai can do this very well, but we found for very tight contractions and for clear water scour, we get deeper scour right here, and it becomes more akin to like a step scour situation. And this was a real bridge. This would have failed a long time ago geotechnically. You wouldn't have that standing like that. But so this is the oblique view, isometric view, and this is a side view. You kind of see the difficulties that we had. That sort of shows the bed forms and the variation. Corner scour, the scour here, depth is easy enough to get, but what's the contraction scour along here? It varies because the flow depth varies along the channel. This is another experiment. We widen the contraction to 0.5, so half the width of the flume. Again, clear water 0.56. We got deeper scour here at the corner. Contraction scour, vena contractor scour is somewhere in here. Before during the experiment and after the experiment. And then after each of these experiments, this is the profile which we got measuring at those locations, which I indicated. Always the deepest scour was at the entrance because of the flow contraction, and this is a LiDAR scan of the full flume, deeper scour here, all the way, and this is a blow up of this region through here. The vena contractor scour is kind of in here. Corner scour is a bit deeper. It's deeper because of turbulence. Turbulence is not handled too well in physical models, which I'll talk about tomorrow. You can see the problems of trying to determine what contraction scour depth is. This is another experiment. I should have had this up here. Live bed, and the shear stress ratio is 1.44. So we have bed forms. The channel width is 0.5. And so this is what we saw. So the original bed was up here. This is the corner scour. The vena contractor scour is in here. Then the flow goes along the channel all the way down to the entrance. And this is an intermediate length contraction. It's very hard to tell what the live bed scour is because of all the variations that one sees. This is along the center line, the vena contractor. Then because of bed forms, you have this variation here. And this is another. So I'm giving you a lot of views. This is where the shear stress ratio is 4. During the process, this is what the flume looked like. So we're in wavy surface, even determining what the water surface profile is not straightforward, these sort of contractions. And then you have the flow separation at the corners. You've got corner scour here. Original bed was up around there. And the vena contractor region is in here. Quite difficult. And just to blow up this a bit more, this is the corner. And so trying to predict what the vena contractor really was, because this is a highly unsteady. A lot of vortices, wake vortices being shed around here, which have a major role in sediment transport. But this was never steady through here. It oscillated, and this was a source of turbulence, which then affected the bed downstream. So the entrance and so forth play a major role. And this, you can see the difficulty in determining what the scour depth would be through a contraction. You know what the corner scour or the vena contractor scour is maybe. That's the problem. Here we plotted, and this plot shows the shear stress as far as we went. Vena contractor scour, corner scour. And the corner scour is very important for abutment scour, as I explain tomorrow. Very hard to predict. This is depth of scour. So vena contractor was shallower than the corner scour. The corner scour, the flow was augmented by the large-scale turbulence that generated in the corners and the flow separation regions. And clear water here and live bed here. So this is again a LiDAR view. So again, you have a view of the close-up region here, the vena contractor and through there, corner scour, and bed forms naturally now forming along the channel. This is where we have the channel width 0.75 of the flume width. This is a clear water experiment. Live bed, deeper scour at the corners, vena contractor somewhere in there, and then the bed varying in depth along the, and I'll go, but this is just a LiDAR experiment, live bed, 0.75, 1.4, the shear stress ratio, the vena contractor scour. So a bridge would cross about somewhere in here. So the depth of scour would be just at the bottom end of the downstream end of the bridge. If you had a wing wall abutment that was sheet piled all the way to the depth, you might get a corner scour like that. If it was an earthfill spill through abutment, it would have failed long ago. And this shows you what the flow looked like when we had 0.75 contraction, the B2 over the B1. Again, the vena contractor has become separated a bit more. Corner scour deeper, you can see from there to there, and vena contractor scour somewhere in there. So you tell me what the contraction scour is. Water surface and bed elevation with this particular experiment, different times during the experiment. And this on the far side, this is the corner scour depth. So the corner scour depth was deeper than the vena contractor scour depth. So these experiments are not easy to do. Contraction experiments are not straightforward to deal with. If I was to do this again, and NCHRP required that the experiments done at a fairly large scale, I would use a smaller scale and do a quick series of experiments, much less sand, quickly get a feel for what's happening. Then I would design a larger experiment. And then maybe use a calibrated, Young Lai is very good at this, U2 RANS 3D unsteady flow model to capture the flow. And I wouldn't use a flow 2D, or I wouldn't use flow 3D for that matter, either on something like this. So we've a ways to go yet with numerical modeling of these, and physical modeling too of these. Anyway, this is LIDAR, where you end up as high, live bed as high as shear stress ratio of 6.25. That was pushing it as really as the other limitation is what flow can you push through the pumps. That shows you through the contraction, 0.75, vena contractor scar somewhere in here, and the corner scar, 45 degrees, which is quite common for wing wall abutments to use. These are typical concrete vertical wall abutments. This sort of shows you what the flume looked like. So that you've got quite big corner scar here. You can see the difference, and the vena contractor scar was somewhere in here. Again, intended just to give you a quick kind of view. So you can see vena contractor scar, corner scar. So you can see why they stayed away from corner scar, because corner scar depends so much on the shape of the contraction. Contraction scar you can get by theory, shear stress velocity, shear stress ratio, I should say, narrower channel, but it's all over the place if you look at it. So what do you take is the depth of contraction scar there. These are for mild contraction, 0.5 ratio. Vena contractor, corner, so quite a big difference between the two. And the difference is due to the turbulence, which is much stronger in the physical model than reality, as I'll show tomorrow. And this, again, just is a composition of various images. The vena contractor right through here. So you have a the flow contracts right down here and reattaches and flows down the full width. Narrow bridge just crosses somewhere over here. You have a flow separation zone, which depends on the shape of the entrance here. So if we had a spill through abutment, we wouldn't have as big a separation zone, I think. And this shows you an oblique view and a side view. Gives you a view of the different contraction ratios with the same shear stress value. You get a lot of differences. And this is an intermediate plan view, intermediate contraction, elevation view, initial bed, final bed, something like this. We think, and I'll show maybe next, Clearwater scar follows this path. If you were you're up to here in the main channel, if you go Clearwater scar on a floodplain, for example, you don't have much sediment transport on the floodplain because of vegetation and so forth. You might have Clearwater scar. You continue up this curve here. For live bed scar, we go off here and then we drop down, as I'll show soon. And we drop down because, as Pierre indicated, the mode of sediment transport starts to change when the shear stress ratio changes. And so that changes the whole flow field. The different quartiles, the average height. We looked at all these, how best to try and present the data. We measured dunes, dune heights, centerline profile, look zigzaggy like that. So what do you take as the contraction scar? You have something like that. If you take as the contraction scar depth, this particular image just shows a blow up of the vena contractor region here. So this translates to this. So you've got bed forms, you've got the corner scar, vena contractor somewhere in here. You have variations. You take L, which is this length here, the length of the vena contractor. But you're never quite sure, it's not exactly one spot necessarily, or one cross section that we could best determine, because these dunes also generate turbulence, which lead to scar depth variation. This is the main scar in the vena contractor region, went that way. The average scar depth plot up. We tried all sorts of plots like this for different contraction ratios through here. This is near the reattachment zone back here. We measured all over the place. My main point. What we found, if we had to modify the HEC 18 equation for contraction scar, which is very important for estimating the abutment scar, we had to add a coefficient for that vena contraction, that narrowing, which was narrower than the contracted channel. We included that, and this depended on the shape of the entrance. So we put that in this particular HEC 18 equation. This is the K value here for different contraction values. And we did a dimensional analysis, and we plotted the width of the channels times Froude number. We got that sort of, this is before and this is afterwards. This is pre-scar, more contraction. After scar, things kind of relaxed. The opening area opened up. Lawson and Alawi, his student, did some experiments at a very small scale, and they got this trend. So increasing shear stress ratio, depth of scar over Y1. Now, what do you call Y1? Basically determined. You reach Clearwater beyond, or the Clearwater limit, and if you get live bed scar, the scar depth drops off. So further experiments are needed. This is the curve that we found for live bed scar, for Clearwater scar up to around here. And then the scar depth over the normal flow depth drops off like this, just like a bridge pier scour. And it drops off because of you've mobilized more of the approach flow sediment. You've changed the mode of the sediment transport, fixed the flow field, fixed the scour depth. So if you mobilize the entire bed of the upstream channel, you would just overwhelm the scour. But doing these experiments at large scale are very difficult to get the flow capacity, the flume size, and so forth. Maybe they're better handled eventually numerically. But to get this sort of long-term trend, basically the mode of sediment transport changes. You keep increasing this is basically shear stress ratio, should be on the bottom here. You keep increasing the shear stress ratio, you change the mode of sediment transport. That changes the scour process. Contraction scour, which occurs at most bridges that have abutments that encroach over the floodplain, sometimes into the channel, certainly occurs in natural channels where you have naturally contracting and opening changes in geometry of the channel. So more work is needed than what we did through here. If I was to do this experiment again, if I was to write the NCHRP proposal request, I would have first phase one, do small scale experiments to see what's going on, then design the big scale experiments, because you don't design big scale experiments and not knowing what you're doing. Also, we did use numerical modeling because we had non-uniform flow. We increased the length divided by the width of the approach channel. We could see how the shear stress varied a bit. So our experiments ran up to here, but if we increase the length, which we only have flume capacity for a certain length, this is how the shear stress would vary. We assumed that this was good enough to determine what was going on for the different experiments. Also, we used large-scale POV to sort of identify the vena contractor. I had another master's student get the width there divided by the width of the narrow channel, and through dimensional analysis we combined it with Froude number. This is dimensionless, this is dimensionless, that's dimensionless. We got these sorts of plots. And so for a typical bridge, you don't use the B2, you use the narrowed part, the vena contractor part, and the KV values. And we have a set of KV values which we would suggest, but more work is needed for different types of abutment entrances. This is pretty tedious work. A lot of laboratory work is not glamorous. Shoveling sand, repeatedly doing experiments, collecting data is not glamorous work. And so you often have a lot of disappointed PhD students until they finally see the thesis all together and they think, oh, wow, that's pretty good. I did all that. This is the modified version of the equation. The question is, well, what y should you use? At the moment, they use this y, which is part of an M1 curve, which is not necessarily accurate. This is a dependent variable. You should use the normal flow depth. On the other hand, this is for many channels. It's a fictitious value, but you can kind of calculate that. It depends on the channel geometry, the roughness, and so forth. Determining what the contraction scour is when you have a non-uniform flow over the top. Choking occurs at this downstream end first, because you have the resistance of this to add to that. Modified design relationship, we would put YN1 here and KV here. Use that to estimate a contraction scour. First of all, we have short contractions, which are typical of bridges. Intermediate contractions, yes, they can occur, but they're more theoretical. The control is downstream, so you're going to get choking downstream before you get choking at the entrance. And long contractions, which are highly theoretical. They can occur in theory, but they don't really occur that often. But Lawson talks about long contractions. Straub and others talk about long contractions. They don't know what they're talking about, in my opinion. I wouldn't trust their data. As I indicate through here, I give some details here. I try to highlight in blue intermediate length contractions where you have the contraction exceeding the length of the vena contractor. So reattachment occurs to the channel. There's some definition of intermediate contraction. Define the approach flow, whether you have clear water or live bed, in terms of the flow depth of the approach channel. But you quickly run into backwater. This is a classic backwater experiment where you have a contraction. Most textbooks you find flow channel is contracted so much. What is the flow depth? We modified the Hick-18 equation using this vena contractor, which gives a little bit better value, at least for the data that we had.